Hello, good morning. We'll continue with the Fourier series representation of periodic signals. In this case, we'll consider what are the applications of this Fourier series. Myself, Dr. Shaila Dinkar Apte, and I'm generating these videos for better understanding of the students and new faculty members. So, Fourier series, as we know, we represent it for periodic signals in time domain. So when we take a periodic signal in time domain, what are the frequency contents? The frequency contents will have the fundamental and the number of harmonics. So the corresponding spectrum, if we plot, this spectrum will consist of discrete components corresponding to the fundamental and the harmonic terms. So you understand that even though the signal in time domain is periodic, the Fourier series representation will be a discrete spectrum and it will be aperiodic. Now let us see what are the applications of Fourier series. We know that in communication systems we use modulation and many times we are using pulse modulation. So in this case the carrier signal is a pulse train. So we must know how the Fourier series representation will be for this periodic pulse train, and that we can write in terms of either exponential Fourier series, or we can also write it in terms of the cosine and the sine functions. So here I am assuming that we are representing it as the exponential function. So xt will be written as summation k varying from minus infinity to infinity x of k e raised to j k omega 0 t, where xk are the Fourier series coefficients and the values of k will vary from minus infinity to infinity. It will not be periodic, it will not be repeating itself. Now let us consider the rectangular pulse train, and we want to write the Fourier series expansion for this. Now this particular Fourier series we want to write for a periodic pulse train, and this periodic pulse train has period equal to capital T0 and it has a pulse width given by capital T. So how xpt is represented? It is equal to a between minus t by 2 to plus t by 2. Is that right? And equal to 0 otherwise. This we are writing it for one period of the periodic signal. Okay. Now let us see how Fourier series can be represented. So we write the corresponding coefficient Cn is equal to, we use directly the formula here for Cn is equal to 1 upon T0, that is the period, and you have to integrate over the complete period. So minus T by 2 to capital T by 2 xpt, this is the periodic pulse train, exponentiation e raised to minus j 2 pi nt upon capital T0, where n will run from 0 plus or minus 1 plus or minus 2 and so on up to infinity. So 1 upon T0. Now this particular xpt periodic pulse train is existing between minus t by 2 to plus t by 2, which is supposed to be the pulse width of the pulse, and the value is a and equal to 0 otherwise. So this is for one complete period that we have represented. So when we integrate over the one complete period, 1 upon T0 integration. Now the integration will be replaced from minus T by 2 to plus T by 2, because this is supposed to be the pulse width. And how the xpt is, it is equal to constant equal to a. So I represent in place of xpt, I write a exponentiation of minus j 2 pi nt upon capital T dt. Now this a will come out obviously. This T0 will cancel with the corresponding term that comes out of this exponential, that is 2 pi t upon capital T, 2 pi n upon capital T. So upon that capital T0 will come in the numerator and it will cancel with this T0. Okay. So there will be a coming out and then this n pi will be coming out. Now this 2 we will see that it gets cancelled, because when we write the exponential term, exponentiation, it is integrated between minus t by 2 to plus t by 2. So when I write plus t by 2, it will be minus j 2 pi n capital T by 2, so that 2 will cancel upon T0 minus minus of minus t by 2. So minus j 2 pi n t, in place of t I will write capital T by 2 but negative, so it will become plus term. So I'll have upon t0, so I will have negative of e raised to minus j 2 pi t upon t0 minus e raised to minus e raised to j minus j 2 pi e raised to minus j pi n t upon t0. So that particular term e raised to j something plus e raised to minus j something divided by 2j is what is called as sine function. And this j, when it comes out, that j will also be getting cancelled, and with the negative sign it will become just sine. Sine n pi t upon t0. This you can solve and check whether you get this particular answer. So it is a t upon t0 into sinc. So when I write sinc function, in place of pi into x, I will write sinc of x, right? So I will write a t upon t0 sine of sinc of n t upon t0, right? N t upon t0. So this pi will naturally not appearing, it will not be appearing in the sinc function. Pi will not be appearing in the sinc function. That's all. Now let us see how to interpret this equation. Xk, the corresponding coefficients, is a upon n pi sine n pi t upon t0. So a t upon t0 sinc of n t upon t0. Put t upon t0 as 0.1. If t upon t0 as 0.1 and if I put n is equal to 10, it becomes sine pi. That means the function again becomes 0 at sine pi. So this indicates that the first zero crossing for the sine function will occur at n equal to 10. If we have t upon t0 as 0.05, on the other hand, first zero crossing will occur at n equal to 20, because at n equal to 20, n into t upon t0 will become equal to 1, and it is again sine pi. So again it will be equal to 0. So that is the first zero crossing of the sinc function. How this sinc function would look like, magnitude of the sinc function, how it would look like. This is the nature of the sinc function. I am writing the magnitude plot of the discrete function. That is why, even though this particular function is negative, actually sinc function is varying like that. But when I plot the magnitude, all corresponding this such functions will be represented by the positive values. Okay. The first zero crossing here occurs at 10 because t upon t0 is 0.1. In this case, it is equal to 0.05. So the first zero crossing occurs at t equal to 20. N equal to 20. That is t upon t0 equal to 0.05 and n is equal to 20. Then there will be a corresponding sine function represented as sine pi. So it will have a 0 value. Now how you can draw the conclusions for this rectangular pulse train? Now let us say, let me assume that t is kept constant. What is t? T is the pulse width. If I keep the pulse width constant and t upon t0 is reduced, then actually t0, that is the corresponding period of the corresponding function, increases, and when capital T0 increases, the spacing between these lines increases. Now in this case, we have not used this particular variation, so it is the corresponding variation is not seen in this case. Second case is visible here. If we assume that t0 is kept constant, that is the period is kept constant, and when t upon t0 is reduced, t upon t0 now becomes 0.05, then actually capital T increases, that is the pulse width proportionately increases, and the first zero crossing occurs farther away. Right, this particular case is seen over here. Let us see how to find the Fourier series coefficients. If it is an even function of time, if the signal or the pulse train is even function of time, only the cos terms will remain. And if it is the odd function of time, only sine terms will remain. Now in this case it is the odd function, so only the cosine terms will remain. Now how to write the corresponding equation for the cosine terms? Cosine terms will be written as 2 upon t0 t to t plus t xpt cos n omega t dt. Right, and bn, these are the coefficients for the mm, odd functions, and in this case this is correspondingly for the sine term, and in this case you see that the sine term reduces to 0. And what happens to the cos term? 2 upon t0 integration. So in this case, what is the corresponding function? It is a. It is varying between minus t by 2 to plus t by 2, or it can be written as 2 times 0 to t by 2 because it is symmetrical. So I write 4 upon t0, 0 to t by 2, a cos n pi n omega t dt. So 4a sine n omega t upon t0 n omega, integration carried out between 0 to t by 2. So it is 4a sine n omega t by 2 t0 n omega. So I can write it as 2at, 2a capital T. So when I write capital T here, there will also be capital T in the denominator, and this I can write it as the sinc function then. So this is a sinc function, and then I have 2a t upon t0 as a constant, and after that I will have a cosine representation. So only cosine terms will be there, and sine functions, the sine corresponding sine coefficients will be giving rise to a 0 value, and this is a constant value, that is the DC value. It is equal to AT upon T0. So how we write the final expression for Fourier series expansion? We can write it as AT upon T0 is a constant term plus n varying from minus infinity to infinity, but not n not equal to 0. For n equal to 0 we have written this term, and for n not equal to 0 it will be a sine function as a constant value, and actually it is the cosine term. These are the coefficients for the cosine term. So only cosine terms will remain and sine terms will result to a 0 value. Conclusions for the Fourier series. Only cosine terms exist for the waveform having even symmetry. When the function has odd symmetry, the Fourier series contains only the sine terms. That you can remember. So while calculations, if you go wrong and if you are getting cos terms in the odd function, then it is wrong, you can understand. Even though the signal is periodic in time domain, its Fourier series representation is aperiodic. This I told you in the very beginning. So let us consider the Fourier series for the signal below. This signal is a rectified sine wave, and it has a period equal to 1 in this case, and it is symmetric, and you can say it is the even function of time. In this case the period is equal to 1 second. So how we write xk is 1 upon t, that is the period, integration over the complete period, xt e raised to minus j k omega t dt. This is the formula. So how we calculate it? Here we go. So xk can be written as, this is even symmetry, so calculate only the cosine terms. No need to calculate the sine terms. So integration 1 upon period, period is 1, integration 0 to 1 sine pi t e raised to minus j k 2 pi t dt. Okay, sine pi t is the corresponding xpt, corresponding function, periodic function, which is supposed to be the rectified sine wave. So if I expand this, e raised to j pi into 1 minus 2k into t divided by 1 minus 2k j pi. So I am combining this sine pi t, I am write it as e raised to uh, j pi t minus e raised to minus j pi t upon 2j. So that 2j is coming here, and this e raised to j2 pi t is combined with this e raised to minus j k 2 pi. So this becomes the term e raised to j pi 1 minus 2k into t divided by the same term will be coming in the denominator when you integrate into j pi. Now this j will cancel, it will become minus 1. So there is a minus 1 here. So this is e raised to minus j pi. Here it will be 1 plus 2k. into t divided by 1 plus 2k into j pi. Integration obviously between 0 to 1 because it is the period. So when you solve this entire thing, you will find that the term comes out to be 2 upon 1 minus 4k square pi. So this is the value of the corresponding exponentiation term for k not equal to 0, and k equal to 0, it will be equal to 2 upon pi. Is that right? So I can represent this as xt, I can represent it as 2 by pi plus summation k varying from minus infinity to infinity, obviously not for k equal to 0 because k equal to 0 the term is here. 1 upon 1 minus 4k square pi e raised to j 2 pi kt. These are the coefficients. Now if I want to calculate the cosine and the sine terms, here only the cosine term will be there and sine term will be 0, as you can understand. So cosine term you can just calculate. Similarly here xpt you write it as sine pi t cos of 2 pi nt and then integrate it accordingly, and again you will get 4 upon 1 minus 4n square into pi. This is for all n. So finally the representation will be like this, with a cos term only remaining and the sine term becoming 0 for all n, because the corresponding function is the even function of time. Now if you want to represent this Fourier series as the spectrum or the spectral lines, then it will be represented like this. So this is the Fourier series spectrum, this is the constant term, and for all n the corresponding values will be negative because 1 upon 1 minus 4k square. So as k increases the corresponding value becomes more and more negative, but the value will go on decreasing. So this is supposed to be the plot of the spectrum for the signal. This is how, given any periodic waveform, you should be in a position to calculate the Fourier series coefficients for the cos sine terms, or you can directly write it for the exponential series. Right, you have to just use the formula, put the value of the corresponding signal, and then evaluate the integral. I hope you have understood. Thank you so much.